This conference will now be recorded.
So the purpose of the webinar. So the main purpose of this webinar is to discuss the architecture challenges and the use of FPGAs in complex electronic systems. So what exactly are those challenges? So what that means is the partitioning, the sizing, the selection, and mapping. So what does that mean? So what it means is in the FPGA we have to design the FPGA cores and the FPGA fabric. So when we are trying to implement an application using FPGA, we have to select the right number of resources, the right way of partitioning, so that we will know what all sequences has to be done on the FPGA core and what all has to be done on the FPGA fabric. So basically, what we have in an FPGA core is that will be the Cortex A series processors along with the RPUs, the GPUs, along with the cache coherence units, and on that FPGA fabric, which we'll be using to run a different set of operations. So if so, it's extremely important that we design both of these units to accurate level. So how do we cope up with the challenges in designing those? That's where the system level simulation is going to come into the picture. So what we use the system level simulation is for designing the FPGA with right amount of resources and the right partitioning and the sizing features. So let's let's say we are designing an FPGA, and we are having the number of PL, the logic units are set to as 1. And now if we are having an application where we are running certain set of tasks on the fabric and certain set of tasks on the core. Now if the set of tasks which are running on the core is not as required as such, then that is an extremely wasted resources. So what does that mean? So for that, for a easy understanding, let me take you to an FPGA model. So this is an Xilinx UltraSync plus MPSoC model. So as you can see here, we are having the MPSoC over here, and then we are having a PL hub over here. So this is where the fabric has been designed, and this is where the cores has been designed. So for a easy understanding, let me double click here so you can see the parameters which has been designed. So as you can see here, we are having a real-time processing unit, and the RPU is having two types of operation, the split mode and the lockstep mode. So the split mode, operation mode, that is the default mode, or like the split mode can be also called as performance mode. So what happens here is each core operates independently. So if we go inside the MPSOC, which we have been designed over here, we can see the detailed implementation of this Xilinx model. So what exactly that means is we can see here we are having an application processing unit over here. We are having the real-time processing unit over here. Then we are having CCA unit over here, and then we are having the Snoop control unit over here. So we designed all of this to match the specifications given on the data sheet and link up with each other so that at the end we are getting a perfect running model. So now at the bottom we are having a behavior flow which states what all data has to be sent to the PL and what all has to be sent to the processor cores. So accordingly, we are going to get a result. We are generating the statistics. For example, we are generating the power here. We are generating the latency over here. So I am going to run it and show you the results. Let's just so this one window over here. This is plotting the power. As you can see, it is plotting the average and miscellaneous power. And this one over here, this is the behavioral flow latency, which means the latency for the whole process to complete. That means the traffic generated, then it interrupts the APU units, then it goes to the PL, then it goes to the on-chip memory, and then it goes to the DRAM unit. So for this whole process to complete, the latency has been calculated, and this is the plot which has been obtained. And this over here, it is the latency for the A53 cores which has been designed in the application processing unit, which is inside this APU, which is inside this piece of unit. So as you can see here, each time an interrupt is being generated, triggered, it is going to come to the GIC and it is going to trigger a specific code as per the application, and then it is going to look up to the cache unit, and then it is a cache miss on L2, then it is going to go through the CCI and to the external memory, which is the DDR. So we are going to go back to the presentation. Yeah. So once we have the FPGA model designed, we try to come up with different things like what are the so what we have to come up with is the metrics that we have to evaluate. So in the case that you have which I have shown you before, it had few of the designing cases for such we are focused on was the latency and the power. So in this case, what we are focused on was latency and power. So similarly, if the customer wants to focus on throughput, then we have to come up with the cases where the throughput will be generated. So now the next consideration of this webinar is to optimize the applications which are run on FPGAs. So optimization in the sense the user might want a case where the latency has been optimized or the power has been optimized, or a case where it can run thousands of test cases on the parallel and still come up with a quite reasonable response time. And all those are the cases that we are going to be dealing with. So now quite a bit about the company itself. The Mirabilis Design was founded in 2003 and it is based in Sunnyvale, California. The development and support centers for the Mirabilis design can be found in US, India, China, Korea, and Czech Republic. So now, as you can see here, there is quite a bit of graphics provided in this page. All these are the products which has been designed with the help of VisualSim, which is the tool provided by the Mirabilis design. So VisualSim, which is the tool which is used for modeling and simulation. So now, why exactly does all these customers use this VisualSim tool? It is because VisualSim provides an extensive large library of IP units. So what exactly that means? So that what that means is the customer they just have to drag and drop these IP units into their design and integrate it quite easily. The user doesn't have to build any of the IP units from scratch. So now we are having the design flow. So over here we are having the sensors, IOs or cloud, which is gonna feed in the data over to the FPGA units. So if you're considering an DNN application, deep neural network application, so then um, we can actually have a maximum of 8 FPGAs connected to a PCIe slot, and then according to the application, we can partition that application and then send them to each of the FPGA units. So over here, we are having the data generated and sent to each of the FPGA cores, and then this FPGA cores handles the deeply pipeline and hardware accelerated operations. So how does this FPGA fit into AI or ML or DNN applications? So this is quite so. As you know, an FPGA is a generic tool that can be customized for multiple users. Modern FPGA works similarly to an application-specific integrated circuit. So when reprogrammed properly, FPGAs can match the requirements of particular application that is just as regular ASIC. So the current generation deep neural networks, such as RxNets or VGG, rely quite heavily on dense floating point matrix multiplications, which is well suited for GPUs. Because of this, GPUs are widely used for accelerating DNNs. But as we know, the FPGA units are advancing day by day. So, meanwhile, DNNs are also evolving. For example, the recent innovations in sparsity and compact data types result in major leaps in algorithmic efficiency. However, this also means that there is an extreme irregular parallelism which has been resulted. So this extremely customable parallelism which has been resulted as a result of DNN cannot be achieved by using general GPUs. But that is not the case with an FPGA. The exponential growth in digital data, such as images, videos, and speech, is driving the need for analytics to extract knowledge from the data. So the FPGA, so meanwhile, if you compare an FPGA to a GPU, you can know that the GPUs provide superior energy efficiency, which is performance per watts, than GPUs for DNNs. So, is it actually necessary that every DNN or every application be implemented on FPGA alone over GPU? No, no, that is not the case. So, how do we decide that certain applications can be run using FPGA and certain cannot be run using FPGA? That is where the system level modeling comes into the picture. So, what exactly does that mean? What that means is even when designing an FPGA, we have to decide what all processor cores has to be used, whether A53 or the RPU units such as the R5s, or like in what mode of operation has to be used, whether it be lockstep or split mode operation, all those comes into picture. So we are using the visual sim for selecting the right hardware and selecting the right operational sequences. So over here we are going to discuss the emerging technologies. So one of the most promising technology which is coming up is using FPGA as an FPGA based acceleration as a service. So that in the sense we are offering this FPGA service as a cloud-based service. So what does that mean is, as we can know, the recent innovations from Intel, which is known as F1 instances, and from Microsoft, which is known as Brainwave, they are implementing the FPGA-based acceleration as a service. So what what does that mean is when what it means is it is integrating a large number of customers around the world to chip in their ideas and then use the resource which is provided via cloud services. So with implementing this FPGA based acceleration as a service, we can bring the cost down to a reasonable amount, and we can use this, and the application of using this is enormous. For example, it can be used for in medical field for curing cancer, or as simple as it can be used for image recognition. Now the next is comparing hardware accelerators versus processors versus FPGA. So there might be an application where you are having a choice of choosing between simple hardware accelerators versus the processor cores versus the FPGAs. Each one of them, so as you can know, FPGA can be hugely customized and can be reprogrammable very easily. So now the challenges that the customer can be faced can be quite grouped into two: exterior factors and the interior factors. So the exterior factors depend upon the memory access, sensor input, and connected devices. And the interior factors are quite depend upon what we decide the model to be. So it is going to be depend upon the processing requirements, connectivity between subsystems, and the software or RTOS isolation. So the metrics that are of utmost importance in our design here is the time taken to complete a deeply pipelined application, which is going to give the latency and which is one of our concerns here. And one other metric that is of focus here is the throughput, and another one is the power consumed per task. So these three throughputs, if we are optimizing these three metrics, then we can say that the model which we have designed is going to do quite well in real-time applications. So since we are, so let me take you to an application which has been supported by the Visual Sim tool, which is called as post-processing unit. So I am gonna show you a model. Um, Let me take, this is quite a simple model. We are having a traffic generator which is going to generate a traffic, and it is going to feed into a queue here. So after a certain while, for the first one it is going to flow through, and over here we are doing a processing. So now we are so there are like different stages of modeling. At first, we'll be designing a stochastic model, which will be having delay blocks. And then at the later stage, we'll be replacing those delay blocks with cyclic rate models. So right now, this is a pretty generic model. So now we are having a pretty simple model over here. So now, if you run this model, you can see the results generated. We are having a latency plot, and then we are having a statistics plot as well. So now let's say you want to run this model over to tens or thousands of cases, and then compare the results on a single screen. So that can be done with the help of the application known as the post processor. So over here we run the same model that we run this model, which yeah, we run this model for three different cases. For the execution time, for the first case, the execution time was 2.5 and the input rate was 1.0. And for the second case, the execution one was 2.0 and the input rate was zero point 0.8. And for the third case, it was 2.5 and the input rate was zero point 0.5. So if I am going to click on view all traces, you can see here the latency which has been obtained for the three cases has been overlapped onto each other and can be viewed on a single screen. So this is one of the advantages of using Visual Sim, where you are getting a lot of applications on a single platform. Now we are going to deal with some of the basic definitions over here. So the architecture exploration. So we are using the Visual Sim tool for architecture exploration, where we are dealing with optimizing system specifications to match the requirements. Over the right hand side, you can see the model which has been designed for this purpose. So the specification which we are dealing with are the processor speed, topology, and the arbitration. So now, according to that specification, we have to match the requirements such as timing, energy, cost, weight, and efficiency. So, so over the bottom right, we can see the graphs which have been plotted over here. And according to the specification and requirement, we are going to do three types of analysis, which are performance analysis, power measurement, and the functional correctness. So what does performance analysis mean? So that means we are going to analyze the buffer size or the utilization, the throughput, and the response time taken by the design that we just now implemented. So what importance is it having? So let's say we are having an application where the buffer size is of utmost importance because the buffer size can be costly. So keeping the buffer size to minimum is what the user might entertain more. So that is one of the concerns that we are having. And then the utilization. So if you're having a resource or like a memory, and if the utilization is quite less, then we don't need that much amount of memory. So then the memory section can be cut down quite well as well. So and then we go to the power measurement. So it is quite important to keep a track on power consumed by different units. Why is that? It is because if you're designing a mobile unit, then it is going to heavily depend upon the battery, which let's take the example of a mobile phone. it will be having 4000 milliamps. And if we are having designing an application which is getting up the power quite fastly, then that is not desirable. So we have to check all those things when we are designing a model. And the functional correctness. So in the functional correctness, we will be checking on the arbitration, software task, scheduling, and the task graph. Say about Visual Sim, we are using Visual Sim for the system architecture exploration. So the system architecture exploration can be done on three domains: hardware, software, and network. And over these three domains, we can do the analysis on four different sections. It can be done on performance analysis, power exploration, failure analysis, and function analysis. So in performance analysis, we will be dealing with the buffer occupancy, the latency, the throughput. And on the power exploration, we'll be dealing with maximum and maximum power maximum power utilized, the average power average power used, and things like that. On failure analysis, what we'll be dealing with is what is going to happen to the model if some of the links fails. What if some of the cores is not performing as it is supposed to be? And then we are going to do the functional analysis as well. So over here we are having what we are having here is the IP blocks or the library which has been supported by the Visual Sim. As you can see here, we support an extensive library which from the left it is going to go from stochastic to the cyclic rate library blocks to the right. So for example, we are having the Corelink, network on chip, the DMAs, the rapid IOs, the ARM processors, NVIDIA Drive PX board, TPUs, and so on, so on. So it's having a lot of custom built blocks. So the benefit of this library block is that when the user, let's say the user is having an application or a model which is using um, AutoSAR or an ARM A53 processor. So all of those has been implemented and has been integrated to the library. So all the user has to do is go to the model. I mean, I can just show you. You can see here or on the left hand side, this is the library blocks. And you can just, if you want to take um, if you want to calculate the power, you can just go over here and then drag and drop a power unit and then configure the fields over here such that it is going to match to the requirement and the fields which has been designed. So now over here we are having some of the design challenges which can be faced while designing a product. So unpredictable timing and behavior. So what does that mean is over on the right hand side we are having two CPU units, an I/O and a DSP unit, two buses which has been interconnected using a bridge. So at first we are considering a single application where it is going to run on CPU one and I/O. So now there is no contention of resources. It is going to go through from the data from the I/O. It is going to go through the CPU one. From the CPU one, it is going to go through DSP, and then it is going to come back to the I/O. So now let's throw in another application. Now there is a contention. So this are this contention and this limited resources and scheduling and arbitration has to be taken care in case we are designing an accurate model. So over here we are having a graph which shows the latency or the response time when we used two different buses. So one bus, we are having two graphs. One is in red and one is in blue. The red one shows the latency or the response time obtained by using a slower bus which is at 200 megahertz, and the one at the blue ports shows the response time which is obtained using a faster bus which is at 400 megahertz. So as one suspects, we expect the 400 megahertz bus to be faster all the time. So yeah, if you're having any doubts in between, you can ask them. We are going to take care of it. Hello, Gabriel Mioni. I didn't get that. Can you type it in English? Yeah. I'm going to come back to you later. Or like we are having a private session. We can just contact us privately, and then I can schedule a private meeting with you as well. So over here, as you can see, we are going to jump back to the webinar. So over here, you can see over the bubble sections, we can actually see that the faster bus is taking a lot of time than the slower bus. So which is quite a bit of a surprise, which the user might not think about it while designing the model. So another design challenge is the impact of software architecture. So let's take an example of an automotive system. So in an automotive system, let's say the brakes, let's consider the brake system. So as you can know, the brake unit is extremely deadline is extremely time sensitive. So what that means is, let's say a car is moving at 60 miles per second. So it is going to have about 3.5 milliseconds before the car has to come into stop. So if you are designing an automotive system, it is extremely important that certain tasks are going to be completed within a deadline. So such is the case with the braking applications. So all those features has to be mentioned or considered while designing a model. So now designing the FPGA models using Visual Sync, it is going to be having two parts, which will be deciding the best partitioning of an application on to an FPGA core and fabric. So as I said earlier, then when we are designing an FPGA model, it will be having two parts. One will be the FPGA core, which is housing the APU and RPU units, and the second will be the fabric unit. And the second part will be the internal operations of the FPGA. So which where we are gonna deal with how we can design an application processing unit, a real-time processing unit, Snoop control unit, cache tolerance interconnect, and general purpose DMAs. And the considerations which has to be taken care of while designing these two parts is that obtaining an accurate timing details. So what does that mean? And obtaining accurate timing details in the sense we have to execute the pipeline applications in a timely basis. So in if you are implementing a DNN or ML application, so then it is of utmost importance that the pipeline, the nonlinear applications, the ReLU or the matrix multiplication has to be done on a sequential manner. Then the latency calculations and the scheduling and the partitioning of the applications has to be also given utmost importance. And then another consideration that we have to take into is the extensive use of the library provided. So since we are already providing you with a massive library, it will be of extremely beneficial if we make use of the library in your model. So, so what are the steps in the designing of an FPGA? First, we need to design an FPGA core and a fabric. So, what? So you will be having, first of all, you will be coming up with the application that you are trying to run on FPGA. So then, according to that application, you will have to decide. You have to decide what type of FPGA you will have to focus on. So let's and the different vendors, for example, the which is provided by the Xilinx, by the Intel, then from the Microsemi. Like there are a lot of options available in the market. So which one are you going to choose? Once you have chosen the FPGA, then it is then we have to design the FPGA core and fabric onto Visual Sync. So why do we need to design this FPGA cores and fabric onto Visual Sim, or like what is the importance of creating a virtual prototype. So that can be shown by using this model itself. So what we have over here is a bunch of interfaces like I2C, CAN, UART, USB 3.0, Ethernet, all of that. And then we are feeding that into the MPSoft. And here we are having the PL hub, where if I am going in, you can see the programmable logic section. Two of them I have provided, and if I am double clicking on that, I can see the parameters which can be changed as per the user wishes. So this is actually this old model says that what is the importance of using a virtual prototype. As a user, you can just build up this virtual prototype within couple of weeks, and then you can run the model on different test cases. See, as you can see, if I am gonna put this parameter to write, then that section is gonna run in effect of in sequence with the right sequence. So if I am putting it as an external, then that means we have to preface the data from an external source, which can be given as SDRAM. So what happens now is it is gonna do a write sequence to an external memory SDRAM. So it is that easy when we are doing system level modeling. So that is one of the key benefits of using system level modeling. So back to the presentation. So now we need to design the FPGA core and a fabric. So we begin by designing stochastic model as per the design flow by using delay blocks instead of the actual ARM processors or the FPGA cores. So what does that mean is this is an extremely accurate model. So what I mean by accurate in the sense, if I'm going to go inside, we can see the processor blocks, which is having the pipeline stages, the 7 stage pipeline, and the I1 D1 cache units, the sizes, the miss memory, and this has been designed to pretty accurate stages. But when we are beginning the simulate, when we are starting to build up a virtual prototype, what really matters is to bring up a easy or stochastic model which is having just the delay blocks. So once we have the delay block stochastic model, we obtain the statistics using the stochastic model. For example, the latency, throughput, utilization stats, and the power usage. So once we have the stochastic model up and running, we are gonna replace those delay blocks and replace it with the ARM processors and the cyclogram memory blocks, GPDMAs, and so on and so on. And once we implement the cycloacrylate model, we are gonna calculate the desired metric values using this cycloacrylate model. And once we have both the cycloacrylate and the stochastic model, we are gonna vary the different parameters, partitioning, sizing, and see how those results change. So over here, we are having one of the earlier stages that we built in the building of an FPGA application. So over here we are having a sensor which is gonna go through a delay block and then go to the fabric and then to the cores. So and we are calculating the latency and the throughput for this early stage stochastic model. So I am going to take you to that model right away. Yeah. So we are having this model over here. So if I am gonna go to the sensor block over here, sensor is nothing but a traffic generator. So it is going to generate a traffic at a rate of traffic rate, and it will be fixed. So that means we are going to generate a traffic at each 1 second, and it will be coming out through this port and then going to the fabric and the FPGA cores. So let me just run this model so that you can see how, yeah, we are having the fabric throughput, and it is having a peak of 1 gigabytes per second, and then we are having couple of statistics, proc1, DRAM, delay time, and then the throughput, how much we are having, and then what is the maximum and the mean time, and like all those has been calculated over here. And then the core latency, it's also been calculated. And then the DRAM read write read enable timing, and then DRAM write read enable timing, and then fabric latency, all those has been calculated over here. So if I'm going to go inside this core, as you can see, we are just having the server block. A server block is nothing but a delay block, which can provide variable delay. So this is our core. Now in this model we have only used a server block. So as you can see, if we compare this model to the model that we have built over here, you can see the clear difference between stochastic and a cycle accurate model. Over here we are using the real processor blocks, and over there we are just using a delay block to get the first design flow up and running. So we implement this design within a week's time, so that we are having a basic flow design flow running. So once we have this design flow running within a week, we then start to replace the delay blocks with the cycle accurate models. So that is what happens over here. This is the We are going to go to the stage 3 over here. This is what we end up with after implementing those cycle accurate features. So over here we can see the earlier sensor block has been replaced with much more traffic generator block, and then we are having a bunch of switches to select to which fabric is it being transferred to, and I'm going to take you to the model so that you can see it pretty much easily. So over here, if I'm going to go inside, we can see we are having much more detailed traffic generators put over here. So we are having this is what we call a script, and which can be used for implementing our logic, whatever arbitration or whatever logic that we want to use. So we over here we have designed a traffic generator which will be totally random, but at the same time it is going to maintain a specific data rate. So if I'm going to run this model, we can see. So as you can see, these are the calculations which can be done using a virtual prototype. The amount of calculations which made using this prototype is huge, like the PS, PL, DMA latency, then the throughput, then the statistics, like the number of packets entered, number of packets exited, is there any packets dropped, all those can be obtained. And then over here we are having the PS processing latency, which means over here you can see the latency of each of the server cores, and then over here we are having the DMA latency as well. So now, yeah. So why do we exactly need the system level simulation? So as you have just seen now, we we can implement our design using, let's say we are having a certain application, and we are using, first we used Xilinx UltraScale Plus, and then we used the same application on Intel Altera or Intel Statics, and then we used the same application to be run on Microsemi. And at the end of that, we are having three different virtual prototypes which run on three different vendors. So now, if you compare the results, such as the latency, throughput, or maximum utilization mean, we can find which one of them actually performed better for your application. And another Another reason for why we are going for system level simulation is for selecting the right hardware for an application. So as I said before, the performance between a GPU and an FPGA for an DNN application has become pretty slim. So how does a user decide to go for a GPU or an FPGA before even fabricating it? So that's where system level simulation comes into picture. Over here, you can just design a virtual prototype, run the application using a GPU, and run the same application using an FPGA, compare both of the results, and then you're having you can easily make the choice then. So another reason for why we are using the system level simulation is to prevent any surprises that may arise after the implementation. And then another test case that we can use by using system level simulation is that we can drive our virtual prototype to cases where it might actually fail. So for example, I'm gonna show you this model again. Now, as you saw over here, we are running this model for a split mode. So what is going to happen if I am going to run it for a lockstep mode? So I am going to run this model. Yeah, as you can see here, earlier the number of cores which was supposed to run was 1, and earlier in the split mode, like earlier we changed the mode from split mode to lockstep mode. So in split mode, we actually needed independent processing modes. So that's why you had, as you can see here, it dynamically got allocated. And so these are one of few of the cases where like we can use system level simulation. Yeah. So this case, like we updated the model during the run. So now I am gonna show you a case where we can see FPGA to FPGA data transfer has been taken place. So what does that mean is in high performance computing systems, each computing node communicates via a high speed serial bus to ensure sufficient data transfer between. But however, each computing node of different bus protocols is difficult to communicate directly. So in such cases, FPGA comes in very handy. So in this case, we are sending the data from one FPGA to another using the Ethernet port. So let me just take you to the model. Also, before that, let me just take you to that model which I was showing you earlier. And I'm gonna just open a new, yeah, this one right away. I was gonna, just, this won't take that much long. This is gonna just show you the importance of why we are using the system level simulation. So now we are having over here this model right over here says the FPGA to FPGA communication through Ethernet port. So I'm gonna run this model and gonna show you a couple of results, which is gonna pop up. As you can see here, it's taking quite a bit of a time, but as you can see, the latencies are getting plotted. So I am gonna let it run in the background. I am gonna show you the functionalities that has been implemented over here. The PL hub over here is having three different ports, which corresponds to high speed transfer, moderate, and low speed. So now, as you can see here, this one over here says that a cache miss happens. So with the help of this system level prototype, which we have designed over here, it is actually showing us what all changes that we have to make and where all we have to make. So as you can see here, there will be a red highlighting which is visible over here. So I'm going to go inside and see which. Okay, so as you can see here, the ARM Cortex A3, the core 3, is actually having an error. So this processor core actually came up with a cache miss during the simulation for the current definition of parameter values. As you can see here, we have defined the parameter values to be so and so. So this is one of the benefits of using a system level simulation, because we can actually see when a cache miss happens, or where the latency goes up high, or where the power performance is undesirable, and make corresponding changes to the model as well. So now we are gonna go to the FPGA, the Intel FPGA. Over the right hand side, we are having the prototype which we have built, and over at the left hand side, we are having the block diagram which has been obtained from the datasheet. I am going to take you to the mod. I'm gonna show you what exactly has been built over here. So we are having a general intercontroller over here, and then the A53 cores over here, and then the cache coherence units over here, and then we are having the L3 interconnect, and then we are having the interfaces connected to it. So, so we are having the FPGA from three vendors. This one over here Intel, and this one is the Microsemi. So for the Microsemi, as you can see, the interfaces are connected over there, and we are having a behavioral flow at the bottom, which is mapping to each of the processor cores, and then we are having the ASP interconnect bus and the switch cases, the DMA for the data transfer, and so on and so on. So we are having the Xilinx, the Intel, and the Microsemi, which are prototypes ready and up to go. And if any of you want to take a closer look at it, you can just contact us, and we are going to send you the models. So now over here we are having a GPU model as well. It is because if the customer wants to implement an artificial intelligence, or like machine learning or DNN application, and if you want to take if you want to see a comparison between GPU and an FPGA, we have got it all in under the same roof. So I'm going to take you to uh, the GPU unit as well. Let me just close up. Yeah, this is the GPU unit. We are having the traffic generator, and it is sent to the warp scheduler, where a sequence of tasks will be executed and sent to the memory. And when it finishes and comes back, the next task will be generated. So I am going to run this model. As you can see here, we are calculating the power over here. We can see here the instantaneous power keeps on increasing. As a result, the average power keeps on increasing as well. And then now after a while, it keeps dropping, and as a result, the average also is dropping. And now an extensive parallelism is being done here, so that's why it's taking quite a bit of time. Let us wait for a bit. As you can see, the latency plots are also being calculated over here. The warps being generated are being specified over here. So as a result, we get the latency stats over here, and we can see here a maximum of 1.5, about 15 microseconds we get for this application, and a maximum of 7 watts of instantaneous power we consume for this application. So now we are going to go through the Visual Sim design flow. So what we need to do is understand the requirements and coming up with the proper design. So what does it mean by understanding the requirements? So if you are designing an application where response time is critical, then we have to concentrate on getting the latency down. Or if you are designing an application where power consumption is critical, then we have to design the metrics as such so that the power consumption will be maintained to a minimum. And then the size allocation, arbitration, and then the comparison of results between the development and the architecture model, and all those things come up in the design flow. So here we are comparing the benefits of using system level modeling and the normal methodology without the system level modeling. So at the end, you can save about 4 to 5 months in designing itself. So if you look at the cost and the time saved, system level modeling is having a huge advantage. It accelerates the model development and it has the highest quality product. So that's for the webinar. And if you're having any doubts, you can ask now. You can use the chat screen, and if possible, use English.